We're at 14.4b, and we're going to be finding the sums of infinite geometric series. If you become lost or confused, we've got 12 previous videos to this chapter that you might have missed something. Just click the description. And we can find the sum of an infinite geometric series. So here's an example of one. This is an infinite geometric series, and it goes on and on and on, and we would keep adding all the fractions as they got smaller and smaller. When we add these together, we'll approach one whole. Look at it as if it were a square, and we added half the square to a fourth the square to an eighth the square to a 16th, and so on and so on. As the fractions got smaller and smaller, we would eventually have one whole square. We'd be approaching one whole square, wouldn't we? I've got a link to a thing called Zeno's dichotomy paradox in the description that you might find interesting, and it'll explain this even more. If we add 5 plus 1/5 plus 1/25, etc., we would slowly approach 6 because of that 5. If that 5 wasn't there, we would slowly approach 1. But because of that 5, we're going to slowly approach 6. And this is true of any geometric sequence that has a ratio as a proper fraction between 0 and 1. So I have a theorem for you. The sum of an infinite geometric series with the absolute value of the common ratio, that r, is less than 1 is given by this formula. The sum is a quotient of a sub 1 and 1 minus r, the common ratio. So we can find the sum of the infinite geometric series 5 plus 5 halves plus 5 fourths, etc. A sub 1 is a 5. Our r, we find it by doing 5 halves divided by 5, don't we? And we can double check it with 5 fourths divided by 5 halves. We see it comes out as a half, and it is less than 1, so we can use that formula right here. And we have a half for r. Our a sub 1 is a 5. That means 1 minus a half is a half. We have 5 divided by a half. We can do a quick little multiplication and flip it around to the reciprocal, can't we? We get a 10. So the sum of this infinite geometric series is 10. Here we've got some alternating signs. We've got 4 minus 1 plus 1/4 minus 1/16. We want to add these up going on and on. A sub 1 is a 4. We find r by doing negative 1 divided by 4. We can check it with 1/4 divided by negative 1. We get a negative 1/4. And the absolute value of that is less than 1, so we can use that formula from the theorem. A sub 1 is a 4. We've got r is a negative 1/4, so we've got 1 minus negative 1/4. Subtracting a negative, we add the opposite, don't we? So we have 1 plus 1/4. That means we have the quotient of 4 and 5 fourths. Flip it around to the reciprocal, multiply straight across, we get 16 fifths. So the sum of this infinite geometric series is 16 fifths. Okay? We can use the formula from the theorem to find rational notation for a repeating decimal. This means we can write a repeating decimal as a fraction. Repeating decimals represent infinite geometric series. So if we had 0.3, I'm missing my bar here. If we had 0.3, and that repeats because of the bar, right? 0.33333. Well, it represents 0.3 plus 0.03 plus 0.003. We keep adding a 0. See that? Why is that happening? Well, if we had 3 repeating like this, 0.33333, what we would be doing is we would be adding a 0 each time so that 3 would come down. See? So each time we added a term, it would have another 0. See that? We could also look at it like this. 0.3 times 10 to the negative first power raised to the 0 power, then raised to the first power, raised to the second power. See that? So we know our a sub 1 is a 0.3, and we find r by doing our division, right? 0.03 divided by 0.3. We can double check it with this one to this one. We get a 0.1. So now we have a sub 1 is 0.3. And we've got 1 minus 0.1. So that's like $1 minus 10 cents, isn't it? So it's going to give us 90 cents or 0.9. And 0.3 divided by 0.9, if we simplified this, it would be 1/3, wouldn't it? See that? We can do it when there's more than 1 numeral being repeated. This was just 3's being repeated. We could do it with a 0.63 that repeats. What we're going to do is we're going to have 0.63 plus 0.0063 because there's 2 digits here. So it would be like this. If we wanted our 63 to keep repeating, we would have to add a couple more zeros each time so that 6 and that 3 could come down, couldn't we? So that's how we ended up with these as our terms. We know a sub 1 is a 0.63. We find r by dividing. We take 0.0063 and divide it by 0.63. We could double check it with this one. We get a 0.01 for r. Now that's less than 1. So now we have 0.63 for our numerator and 1 minus 0.01, which is like $1 minus a penny, isn't it? It's going to give us 99 cents. These are both divisible by 9, so when we simplify it, we get 7/11. So this simplifies to 7/11. See? We're going to learn more about this when we get to pre-calculus, okay? But it is in the Algebra II textbook, so I figured I'd cover it. Now, another thing we're going to cover when we get to pre-calculus, but it was mentioned in the Algebra II textbook, is that we're going to be graphing sequences as a function. So our x is just going to be 1, 2, 3, 4, 5. Our y is going to be the terms, okay? So we can graph a sequence by plotting a point for each term or by using a graphing calculator. So we can graph the sequence 4, 2, 1, half. That's going to be our y values. Our x values are just going to be 1, 2, 3, 4, okay? You can look at it like that's the subscript, can't you? When we graph this, we've got our pairs. We've got a 1 for x, a 4 for y, that puts us here. We've got a 2 for x, 2 for y, that puts us here. 3 for x, 1 for y puts us here. And you can see what this is slowly doing. It's curving towards the x-axis, isn't it? See that? If we have a sub n equals 2n minus 3, we can plug in a 1 for n, then a 2, then a 3. We can do the math. We get a -1, a 1, and a 3. Those are going to be our y values. X is just going to be 1, 2, 3. Look at, we have a linear graph here, don't we? It's going in a straight line. See that? Here we have a sub n equals 10 times 0.8 to the nth. So what we can do is we can put a 1 here, a 2 here, a 3 here, a 4 here. See? For the n. When we do our math, we get an 8, a 6.4, a 5.12, and a 4.096. Those will be our y values. Our x values will be 1, 2, 3, 4. And when we plot them, we can see it makes this curved line. It's approaching the x-axis, but it's curving at where y equals 1, isn't it? See that? So it's a little taste of pre-calculus for you. Our next lesson is we're going to prove mathematical statements. It's lesson 14.5a. And I'm going to show you how to use mathematical induction. Okay? They teach it a lot in pre-calculus. They're going to just touch on it a little bit in this Algebra 2. But keep your mind open, okay? Because it will be helpful to you in the future. All right? I'll see you next time. Bye.